Welcome back to ECE 340. Not very many lectures left. Hopefully we'll still have students as we go through those lectures. Three things that are upcoming and a fourth that I need to maybe get some input on, and that's the final exam review session if you want one or not. It would probably occur on a Monday during finals week, which I believe our final is on Wednesday the 8th from 1 to 3. There's homework assignment 9, which is due Thursday of this week. Homework assignment 10 is due the following Tuesday, a week from today. And your final exam is 2 weeks from tomorrow. Not that far away. Let me know. Haven't yet decided when the final exam review will be. Is it okay to have it at 5-ish, or do you want it somewhere other than that on a Monday? Do you have exams? Let me know. Maybe we'll make that announcement a little firmer later. I want to cover a lot of material. Today I basically want to finish up Fourier transforms. And then Thursday we will talk about sampling, the Nyquist rate, aliasing, things like that. That's the plan. A week from today we'll sort of, I'm not sure, have an overview lecture maybe of the material. Yes. And I think some of you will be missing, and that's why I'm trying to have a different style lecture on Tuesday, but I will record it so that you can watch it and put yourself to sleep that night if you do miss the lecture. I think I'm going to start charging for that because at least it's worth the price of a bottle of sleep aids, right? Whatever that costs, $1 or 50 cents or something for you to watch these lectures. Here's where we're starting. We've now figured out or derived these pairs, these transform pairs, the Fourier transform, which relate the time domain and the frequency domain concepts. Let's look at what happens when we Fourier transform a pulse. Then we want to look a little bit more at this dual nature. And the dual nature is this time and frequency. And if you simply look at the transform pairs, they look a lot alike. And that's where this dual behavior comes into play. And you can sort of see time and frequency. One is the reciprocal of the other. And that bears itself out when we're looking at the results from the Fourier transform of this pulse. If we have a pulse of width tau in the time domain, we will see that the effective bandwidth, the theoretical bandwidth, is all frequencies, DC out to infinity. But the effective bandwidth is the reciprocal in hertz of the duration of the pulse width that we had in the time domain. And we'll hopefully get more comfortable with where that's coming from as we go through. There is a quick way to find the Fourier transform if you're more comfortable with the Laplace transform. If you have the Laplace transform, if it's a stable transform, meaning what? What do I mean when I say capital X of S is stable? What could you do with capital X of S to determine if it's stable or not? Okay, you could start talking about BIBO, but I'm not really worried about BIBO. I want you to just look at the frequency domain representation, capital X of S. What provides a stable system if you now have capital X of S? You can look at the denominator. You only have to worry about the denominator, and you want all of those roots to have negative real parts. You want all of your poles of capital X of S in the left half plane. If that's the case, then you can simply replace S everywhere with j omega. You can evaluate that transform on the imaginary axis, and that will provide your Fourier transform. That's only if capital X of S is stable. And the way that you verify stability is you look at the roots of the denominator. Those produce the poles of your system, and you need those all to be in the left half plane. Nothing on the imaginary axis. We'll then talk about a way to determine if a signal has a Fourier transform. A sufficient condition or sufficient conditions for that to occur are called the Dirichlet conditions. And those are just sufficient. They're not necessary. You can have a signal that violates one or some of those Dirichlet conditions, and it can still have a Fourier transform. But if it satisfies these Dirichlet conditions, then you're guaranteed that it does have a Fourier transform. And we'll talk about what those are. We then will look at Parseval's theorem for the Fourier transform case. And this is really just setting the energy equal to itself. You've got the energy expression in the time domain equal to the energy expression in the frequency domain. That's all that's really saying in terms of Parseval. But now, if you wanted to know what is the energy contained in a certain frequency interval, now you might want to concentrate on this frequency domain version of the energy expression. The time domain, a lot of times that's probably easier to think about for all the energy in the waveform. But the frequency domain now provides you with an opportunity to examine the behavior or the energy content of your signal over certain frequency intervals. You might say, what's the energy content between 10 radians per second and 20 radians per second? Maybe capital X of omega was null or nearly null in that region. Then you can see that there's no energy content in that frequency interval for that particular signal, little x of t. We'll then talk about some common waveforms and their Fourier transforms. You need to be comfortable with these Fourier transform pairs, and there's another table that talks about Fourier transform operations. Linearity, modulation, time delay, those kinds of expressions or relationships between time domain and frequency domain you need to be comfortable with, and that's maybe table 7.2. I'd have to look. That's where I want to go. Let's now remind ourselves of these two relationships before we derive the Fourier transform of a pulse, just to remind ourselves what we have, what tools we are using now to find the frequency content in a time domain waveform little x of t, or how do you build little x of t out of a frequency domain description of that waveform. And these are equations A and B 7.8 in your textbook. What we want to do today to start is find the frequency content in this pulse. And you could write this as rect of t over tau. It's centered at the origin in time at t equals 0, and it then has a duration of tau units or tau seconds, and you could write it as rect of t over tau. And we want to now find the Fourier transform of that time domain signal. From the definition, we can now say that x of omega is equal to this integral, and now we're integrating over all time, t equal minus infinity to infinity, of x of t, our waveform of interest, e to the minus j omega t dt. In this particular case, x of t is given to us by that pulse. And now we know that we don't have to worry about an infinite length of time in our integral. We are simply worried about this interval of support where x is non-zero, and it has an amplitude of 1 in that interval. Our functional form then is pretty straightforward. It's just 1 e to the minus j omega t dt, and we can integrate then from the lower limit of that interval up to the upper limit. Now we simply have to remember how to integrate this exponential, and we've done that before several times recently. We can evaluate at the upper limit and the lower limit. We can push that negative sign inside the bracket. We can push that j inside the bracket. And we now have e to the j omega tau over 2 minus e to the minus j omega tau over 2 all over j. And that would look really nice if we had a 2 down here, but we can't just put a 2 down there without doing the same upstairs. We can multiply by 1 as much as we want. And now this expression in the rectangular brackets or the square brackets should look very familiar. That gives us Euler, or via Euler's relationship, this is what expression? That's just the sign of that argument, omega tau over 2. We can now write, and remember what capital X of omega was. That's the Fourier transform of a pulse of width tau. That's now this 2 over omega sine of omega tau over 2. And we can actually make that fit a slightly different structure. We can pull the omega underneath. Actually, we can pull the 2 underneath the underneath. That's the same. And if I simply multiply by tau, again, in the numerator and the denominator, I now have the same argument in the denominator as I have for the sines argument. And that's this nice structure that I wanted, this sine x over x. And that's the sinc function that we are wanting to get comfortable with. Tau, again, that was the length of time that our pulse was on or active in the time domain. And that's influencing then the argument of our sine and the expression in the denominator, that tau. But we can now say that we have x of omega as tau sine of omega tau over 2 over omega tau over 2. Or we can rewrite that sine as, or sine x over x as sinc of omega tau over 2. We now have this transform pair. That's the transform pair of, in the time domain, this is now our x of t, equal to this rectangular pulse of amplitude 1. We know what this looks like in the time domain. Let's now get a little bit better feel for what this sinc looks like in the frequency domain. Let's now examine the shape, so we're actually finished with that problem in terms of finding the Fourier transform, but let's now examine the shape of that frequency content from that pulse waveform. If we evaluated that at DC, now we have tau times the sine of 0 tau over 2, 0 times tau over 2, and that's 0 over 0, but you know how that's why you did your calculus. Now we can look at the limiting case of that, L'Hopital's rule, and that now goes to 1. So that we now know that at DC, the frequency content is going to be related to the width of the pulse in terms of its amplitude. That's the value then that we will have at DC. Then we can also start asking, this now has sine x behavior over x. So we have to blend 1 over x with sine x. And 1 over x looks like this in terms of a shape in the frequency space. And if we use that as sort of a envelope measure, we can have it downstairs also, or in the negative axis. And then we have to worry about how sine is moving as a function of frequency, and we're multiplying those together. We have sine x times 1 over x. It would be nice to know then, for sketching purposes, where does this sine cross 0? The 0 crossings are going to occur when this argument in the sine function, which was omega tau over 2, when that's some multiple of pi. Pi, 2 pi, 3 pi. L is just our index. And typically we only want to see 1 or 2 of those, and we've had enough in terms of sketching, probably. If we solve that now for the frequency variable, omega, that's the frequency where we will have these 0 crossings. We solve that for omega, and now we have 2 pi over tau times the index L. But we know, if we have kept this in our mind, we know that omega is 2 pi f. Meaning if I divided both sides by 2 pi, I would have the frequency f. Or I could also write this in terms of frequency crossing, or where it crosses the frequency axis. It's now 1 over tau times L. This was radians per second. This is in hertz. And that now gives me a relationship between the time domain duration of my pulse, which is tau, and where in the frequency axis it crosses 0 in magnitude, in hertz. It's reciprocally related to the width of the pulse in the time domain. We can now maybe a little bit more effectively sketch that. First thing I might do is I might include these guidelines that help me bound the envelope of this this frequency variation as a function of the sine of omega. These are now proportional to 1 over omega or 1 over f. And what we just said was if we did it with respect to hertz, this is going to be now 1 over tau. That's the first zero crossing. The second zero crossing is just 2 over tau. And then the third, 3 over tau. And likewise over here. We have the negative of those values. We've located the value at DC right on Q, which was tau. Oh, tau. So now you'll never forget the magnitude of that, right? All you have to do is think motorcycle. Motorcycle, huh? Oh yeah, tau, tau, tau. I don't know. All right, so now you have tau for the amplitude or the value at DC, and it's now going to have this sinusoidal shape bounded by that 1 over x or 1 over omega or 1 over f characteristic. If you don't like my sketching, which I wouldn't argue with, I can't say that it's the best, but you might look in the book at figure 7.1, or I'm sorry, figure 7.9, or you might even look in the MATLAB section. They give you a way of plotting these in MATLAB in the very first MATLAB session, problem 1. So you might look in figure M7.1 if you want a better picture of what's going on with this sinc function, but I think you're comfortable with that sinc function. What does this tell us? What are some observations that we can make based on what we've just derived and sketched? How long or what length was our pulse in terms of time? Tau was bounded, wasn't it? It was less than infinity. It was finite. Tau was just a finite length or a finite non-zero interval. So that a signal or signals that are of finite time duration, that was the pulse, or you might just abbreviate that and say, oh, the pulse was time limited. In theory, what was the interval of frequency where that was non-zero? Capital X of omega, where was that non-zero? That was infinite, wasn't it? So these signals contain infinite or have an infinite frequency bandwidth. Or I might refer to that as infinite frequency content. That's theoretically. Practically, maybe it's something else. But we can also think of that in a dual sense, in terms of trying to understand this notion of duality. Meaning we had a time-limited pulse that led to an infinite number of, or an infinite extent of frequency content. If we now looked at something that was infinite in extent in the time domain, which we've played with now, in the form, let's say one example would be a sine wave. That never stopped and it never started. Well, it was always on, I should say. It was always on. This is now a waveform in time of infinite duration. And that, what did the frequency content of that look like? It was just one line, wasn't it, for one frequency of a sinusoid. This now gave us this line spectra, which we could refer to as a band-limited behavior in frequency. Meaning if I gave you some cosine of 2t and I said sketch its frequency spectra, and maybe I said give me the compact trigonometric form of that, hopefully you are comfortable doing that. How would you draw that? Where's that tick mark on the frequency axis for this example? This is now omega, my frequency axis. Cosine t, cosine omega t, isn't it? So this is now 2. And what do I do here? It's a height of 1, isn't it? It's not an impulse, it's just a height of 1. So that has an amplitude of 1, and that's the frequency content of that sinusoid, that cosine of 2t. What we want to do, though, is probably treat this more from a practical perspective, but first we could just comment that theoretically the frequency content of a time domain pulse spans the entire frequency axis. It goes from 0 to infinity. But if we go back to this picture, in terms of, this gives us our frequency behavior or frequency content of our pulse. Where's most of this energy concentrated? If you had to throw stuff away, what would you start neglecting? You could probably say that, oh, I'm just going to worry about this frequency content from 0 dc up to 1 over tau. That's the effective bandwidth. The other is starting to be negligible, roughly. So that now, in terms of the practical picture of this, most of the signal energy of that time domain pulse was contained between DC and 1 over tau in hertz. If we wanted that in omega, let's say we wanted our effective bandwidth in radians per second. This is now 2 pi 1 over tau, or 2 pi over tau. So now when we're talking about the frequency content, remember those negative frequencies are really more of a mathematical convenience. And if we want to talk about bandwidth, really we want to go from DC up to the positive frequency of interest. And then we know that the negative side will be there, but that's not what we would consider as part of the bandwidth. So you don't want to double your bandwidth by considering the negative frequencies. That's, I think, what could be confusing. Maybe I shouldn't have said anything. But now you need to go from DC up to some positive value of frequency. And that's your bandwidth. And you could refer to it either in terms of hertz or cycles per second or radians per second, which if we went back to our diagram, we could have labeled this as 2 pi over tau. This is now 4 pi over tau in terms of omega radians per second. And this is now 6 pi over tau. Let's just think about this in terms of some examples. And what you're hoping to try to get out of this is if somebody now started giving you waveforms that are maybe effectively this width in terms of their non-zero duration, what do I need my circuit or my system to be able to handle in terms of its frequency behavior? For example, suppose that I am told that somebody is going to give me a time domain waveform that has a pulse that's 10 seconds long in duration. What's the effective bandwidth in hertz? It's 1 over tau, isn't it? So this is now 1/10 or 0.1 hertz. This is now the bandwidth that we've agreed is containing the majority of the signal energy. Meaning your circuit doesn't have to be very fast, does it? It now has to have, if it was low pass in behavior and it needed to not distort that pulse much, if you had a 10-second pulse, then your bandwidth, your corner frequency on your system better be 0.1 hertz or more in order not to change the shape of that pulse very much. What if we now shortened that? And we said, what if in the time domain the pulse width is now 1 second? Now what's the effective bandwidth in hertz? Now it's 1 hertz. It's 10 times as fast in terms of bandwidth. Likewise, if we now just keep shrinking that pulse, let's say that it's now 0.1 seconds, or 100 milliseconds, or 1/10 of a second. Now your effective bandwidth is 10 hertz. And you can now start to see how this can really start to get more demanding of your circuit. If you now are sending pulses that are very short in time duration, that's saying that your circuit better be able to handle higher and higher frequency content. Yes? Well, if your circuit is a little bit lacking, what's it going to do? It's going to distort that waveform, that pulse. And now, instead of being nice and crisp in terms of a pulse behavior, now it's going to be dispersed. And the more dispersed it gets, maybe it's going to overlap. Maybe you were actually trying to send zeros and ones. Now you have 0, 1, 0, 1, 0, 1, 0, 1, but they're all getting blurred. And now your detector is going, I don't know what he has sent me because it's all mashed together. I can't determine whether it's 1 or 0 because they've now all started to mix together. So it could start causing blurring or dispersion, and that may be a problem. But essentially, you're now spreading out your pulse if your system is not able to handle that bandwidth. If you now were sending a millisecond pulse, now you would need 1,000 hertz for your bandwidth, etc. So now slew rate a lot of times is a measure of your speed of behavior in terms of how well can you sort of pass information. And if you have a very short slew rate, that simply is meaning that your system is pretty fast. And that may be one way that you're measuring your system's behavior instead of by its bandwidth, is maybe talking about the slew rate. Are there questions on this pulse? This pulse, you're probably going, why in the world are we spending so much time on a pulse? You can model a lot of things with just a pulse. Even if the top looks weird, you can say, well, it still has this length for a duration, and I can now take the average value of that messy top. Now you know roughly the frequency content of that signal. You know its effective bandwidth is 1 over tau in hertz. And that buys you a lot of useful information. Questions on this? What did I also say that we were going to cover? There's a lot to be covered. I wanted you to be comfortable with this connection between the Laplace transform and the Fourier transform. A lot of the ECE students might be more comfortable with the Laplace. And if you are, then the Fourier transform is not that big of a stretch for certain signals or for certain systems. For example, if I now had the Laplace transform of e to the minus at u of t, and I'm hoping you're starting to get comfortable with this product concept. What's that u of t really doing in this case? It's just turning that signal on. It's really just saying this is a one-sided waveform. That u of t is acting like a switch. This is just a switch, and now we just have to say, oh, I have an e to the minus at behavior for positive values of time. This is really just a switch, and consequently what I have is a time domain waveform that has that exponential decay behavior. What's this Laplace transform? That's 1 over s plus a, which in the frequency domain, if I now said sketch the poles and zeros, now you can see that anytime we start a lecture, I could basically just go the whole semester in terms of connecting it with what you already know. Now I could say, draw me the pole zero diagram. Well, now that you have this transform, 1 over s plus a, you can identify the finite poles and zeros. And that, if it was a system, would be first order. This is now the transform of a signal. So we can have transforms of signals, we can have transforms of systems. And if we're working in the frequency domain, we need to make sure that we're working with both, that we have the transformed signal and the transformed system. Now, if we wanted the Fourier transform, and now I have to try to remember how to draw a cursive F. My whatever writing teacher would probably not be happy with my, probably disappointing more than just my writing teacher. But anyway, here's F, the Fourier transform of a one-sided exponential. That, by definition of that script F, that's our Fourier transform. Now, based on what I said as a goal in the start of the lecture, is it fairly easy to find the Fourier transform of this x of t? Yes, because I've already told you where the pole is, didn't I? And as long as all of my poles were over here in the strict left half plane, not on the imaginary axis, I can now replace all of those s's with j omegas, and I have my Fourier transform. Meaning now I can simply write this as 1 over s becomes j omega plus a. And this was true because x of s is a stable transform, and that then allows s to be replaced with j omega. So anytime you have all your poles well behaved in the left half plane, the Fourier transform is not very difficult to compute. Quick way of finding the Fourier transform. Something else that you might like to know is, when are we guaranteed of a signal having a Fourier transform? And that's where these Dirichlet conditions come in, which are sufficient conditions for a time domain waveform x of t to have or possess a Fourier transform. And these are these Dirichlet conditions. But first, let me just emphasize the fact that these are sufficient conditions, meaning, as a note, these conditions are not necessary. For this Fourier transform to exist. Here, I've broken it really into just two pieces. The first piece is that this time domain waveform, little x of t, is absolutely integrable over the infinite time horizon. What do I mean by absolutely? Do I just mean it's emphasized? It's integrable. Absolutely, it's integrable. Okay, so now we are looking at explicitly the absolute value or the amplitude of this waveform x of t, and we're integrating that. So there's no area under the curve that will produce an infinite area, meaning we now, that is this integral from minus infinity to infinity of the absolute value of the time domain waveform x of t, that integral is bounded. If you can now show that your signal is bound, absolutely integrable, and x of t satisfies this next description, x of t has a finite number of discontinuities and a finite number of maxima and minima in any given finite interval of time. So x of t has a finite number of discontinuities in a finite interval. It also has a finite number of minima and maxima in a finite time interval. If we sketched that, which I'm not going to be very good at sketching, but if we looked at the first one, here's, let's say, a finite time interval. Then what I'm saying is that this would be a waveform that was very discontinuous or not continuous, but it's still, there's a finite number of those in that interval. What we're saying is your signal x of t that you're trying to Fourier transform has to have a finite number of discontinuities in any given finite time interval. Pardon? Could it be discrete? I'm not quite sure. You just have to have a bounded number of discontinuities in any finite interval. Well, most practical systems satisfy this. That's the whole point of this. So that's the first one. The other one is in any finite interval, and again, I'm not going to be able to draw this very effectively. You want a finite number of maxima and minima, meaning you can't be bouncing up and down, up and down, up and down an infinite amount of time, or an infinite number of times in any finite interval of time. So now we'll look at constant values in terms of, and these are just sufficient conditions, aren't they? So now we are interested in if something, so this is basically saying practical signals can be Fourier transformed. That's the whole idea. So now if the signal is unbounded, now it may not satisfy these sufficient conditions, but we might be able to find a Fourier transform of it. So these are just sufficient conditions. We now need to know how do we handle these special cases, and we may just have to look at limiting conditions and apply limits in order to find some of these signals that don't satisfy the Dirichlet conditions. Those are, again, just sufficient conditions for the Fourier transform to exist. Let's now talk about this concept that we've already talked about with periodic waveforms, which was Parseval's theorem. But that was dealing with power, wasn't it? Since we had power signals, now typically these are going to be energy signals. Now we will have the Fourier transform of cosines and sines, and those are power signals. But in general, most of these are energy type signals that we are worried about finding their Fourier transform. And what we're doing here for Parseval's theorem is we're equating the time domain energy, and we'll have some expression for that. And we will simply equate that with the frequency domain energy expression. And this is now Parseval's theorem for the Fourier transform. Which is an energy relationship. And again, this is similar to what we've derived before. If I ask you to calculate the energy of a time domain waveform, what would be the formula? So now if I ask you for the power, we would have to worry about the period, wouldn't we? But now with an energy, now that period we don't have, do we? It doesn't repeat. We do have an interval, a time interval of interest, but what could it be, the time interval? It could go all the way from both ends of time. So now we need to integrate over all time and again, we're talking about this generic energy. It's normalized. Let's say we have a 1 ohm resistor, and X is either the voltage or the current. We're just saying, we'll just agree that whatever X is, we're going to square it, or take its absolute value, square it, and integrate over all time. And that would give us the total energy in that signal. What we want to do is derive the result that we started with in the first of the lecture. Where does that come from? Well, that just comes by playing with this expression and knowing these Fourier transform pairs. What was our trick before? How did we express the absolute value of something squared? We started playing with its complex conjugate, didn't we? I'm just going to start rewriting this in many different equivalent ways. Now what I want to do is express x of t in terms of the synthesis equation for the Fourier transform. How do I build x of t out of its frequency domain content? That's this 1 over 2 pi integral over all frequencies, capital X of omega, e to the j omega t d omega. Let me replace x with that expression, meaning I still have this interval or integral from minus infinity to infinity of x star of t. This is the complex conjugate. And now I want to replace x of t with its inverse Fourier transform, or its synthesis version. We now are integrating with respect to frequency omega. We have the frequency content, capital X of omega, e to the j omega t d omega. And then we have dt. That's just one of our transform pairs. But now 1 over 2 pi is a constant. We can slide that completely out of both integrals. And we're going to now interchange the integrals as long as we keep the right x's or the right, x's or omegas or t's underneath the proper integrals. Meaning, let's now pull that 1 over 2 pi outside of everything. Let's shift that omega integral as far to the left as we can. We now have this capital X of omega. Then we have this integral with respect to time of x star of t e to the j omega t dt. And if I now grouped it this way, that result will give me an omega formula or expression, and this is now d omega. Now what I'm going to do is pull out or use this idea of conjugate. If I pull out the conjugate from little x of t and I pull out a conjugate of e to the j omega t, I can change the sign of the exponent. So that now I have 1 over 2 pi integral from omega equal minus infinity to infinity of capital X of omega. And now what I want to do is I'm going to take this integral that I now have, t equal minus infinity to infinity of x of t e to the minus j omega t dt, but now I'm going to conjugate the whole thing, d omega. And now what's inside this square bracket underneath the conjugate is my definition for the Fourier transform. This now is my analysis equation. This tells me the frequency content in little x of t. That's just capital X of omega, or what I've also been calling the analysis equation. Now if I combine all of those, or essentially absorb that middle integral or that inside integral, collapse it down to just capital X, and realize that I need to conjugate it, I now have that expression. But remember what x times its conjugate does. That just gives me the absolute value squared, meaning I can now rewrite this as 1 over 2 pi, the integral, and now I'm still integrating with respect to frequency. I now have the frequency response of little x of t, capital X of omega squared, d omega, and that's the energy in the frequency domain, which should be the same energy in the time domain. Questions on that? Now, one thing that if you start going further with, let's say, some communication courses, you might be interested in what that frequency response, capital X of omega, absolute value squared represents. What is that? Well, if you look at it, we have a d omega over 2 pi. That's some variable, isn't it? Omega over 2 pi. That's just hertz. We now are integrating something times hertz to give us joules or energy, meaning this expression, absolute value of x of omega squared, must be joules per hertz, or that's like a density, isn't it? That's like an energy density. And that's what's called this energy spectral density. It tells you how much energy is associated with certain frequency intervals. Here's what I'm trying to make clear. Our energy is in joules by definition, and our energy expression that we just derived, now I'm going to pull that 2 pi inside and underneath the d omega. Since that's just a constant, I can do whatever I want with that. But now if we remember, this relationship, now we have something, the integral df. Well, that integral something df, that's just hertz in terms of units. This now, you could say in terms of its units, is cycles per second or hertz. Now we can say that this piece, if we were just interested in it, this capital X of omega squared must have units of joules per hertz, meaning this is now an energy spectral density. And you could actually simplify this. This actually goes back to an earlier question. Do we need to worry about bandwidth and negative frequencies and positive frequencies? If we simply double that integral and only integrate from 0 to infinity, then we can say that the energy is the same as this expression. We could go from DC up to infinity, and now we have the same expression. We now are not dividing by 2 pi. We've doubled that, and we only look at this 1/2 of the integral. Questions on what we've covered so far?
So you're effectively adding up or integrating all of the energies associated with each frequency.
So now you are essentially, in this case, in this expression for the energy, this is the frequency domain energy expression, you are now capturing all the energy content in given frequency intervals. You really, with the differential ideas, you really can't say what the energy is at a particular frequency, but you can talk about energy interval or frequency intervals and how much energy is in this given frequency interval. Maybe what's the energy between, and now I'm going to convert to hertz just because maybe it's easier, maybe between 20 hertz and 20,000 hertz. What's the energy in that waveform? And that's what we would hear, right? Maybe somebody gives you a signal and they say, here's the energy, and then you find out that only 20% of that energy is in an auditory frequency interval. Maybe that's good, maybe that's bad. Who knows what's going to happen with that other part of that signal. May hurt us beyond what we were thinking. Maybe we can't hear it, but it may be doing damage. Other questions on this? Let's now look at some Fourier transforms of some common signals. And what are we really trying to do? What's the Fourier transform? What's the big picture idea behind all of this. What are we wanting to do? We're trying to help us, right? I'm not doing this just to make things confusing or to make you stress. This is to help you understand what's going on with respect to signals and systems. You're trying to now find the frequency content of certain signals. Let's look at one that we already know the answer in the back of the book, which is this decaying exponential. And we've already derived that, right? Well, we didn't really derive it. We just found it because we know decaying exponentials, where's its pole? And now I'm going to say this is a one-sided, which typically all of our Laplace transforms that we've been doing most of the time are just these one-sided waveforms in time. There's our signal. But we could plug this into our formula, and now we're going from minus infinity to infinity in time, but it's not defined from minus infinity to 0, or it has a 0 value. Let's just integrate only from 0 to infinity, e to the minus at, e to the minus j omega t dt. This was our x of t. So that now we are integrating, we can collect all of those exponents into one, and we have minus a plus j omega t dt. Or this is now minus a plus j omega e to the minus a plus j omega t, evaluated at the upper and lower limit. This we can think of as e to the minus at, e to the minus j omega t. But instead of pulling all of our hair out when we're trying to evaluate at infinity, what's the magnitude of e to the minus j omega? It's always 1, no matter what t is. So even though it's bouncing around, we have it bounded in magnitude. This piece is bounded, and now we're letting, if a is positive, this e to the minus at is well behaved, and so we can perform this evaluation at infinity. We're saying, remember that e to the minus j omega t is always equal to 1, and that allows us now to, evaluating at the upper limit, that vanishes. Capital X of omega is now minus 1 over a plus j omega. The upper limit now is 0, minus e to the minus a plus j omega times 0. But now we have e to the 0, which is 1. We have two negative signs, or the Fourier transform of this decaying exponential, one-sided. If I just interchange the order of a plus j omega to j omega plus a, this is what we had already derived by replacing s with j omega. Questions on that? If it's not one-sided, you're setting me up. Let's look at a special decaying exponential. And this one is going to be two-sided. And if we get this one, then we can look at a lot of limiting cases to derive all sorts of relationships. Here's the special exponential that I want to examine. Let me call this x sub 1 of t. I don't want to go too far too fast, so let me just keep this the way I felt good about. This is now e to the minus at with a positive. That I already know how to do, but I said let me introduce the other side, and the other side I'm going to start at minus 1, but it's also going to vanish as t approaches negative infinity, meaning in a functional form this is minus e to the at. Again, a is positive, but time is now negative, which allows this to decay as t marches towards the left of minus infinity. Questions on that? Now, what this is going to buy us, if we can find this Fourier transform, look at what happens as a shrinks to 0. If a shrinks to 0, a is positive, but now it's getting smaller and smaller. What happens, what happens to this shape as a gets smaller? It gets flatter and flatter, which in the limit, what happens? It's just now always flat, isn't it? What happens to this left side as a approaches 0? It also gets flatter to where it's now constant at minus 1. This is now the signum function. And we'll be able to, once we have the Fourier transform of this, x sub 1 of t, we can look at the limiting case on that and find what happens when we have a signum function's Fourier transform, which is minus 1 when we have a negative value of time and positive 1 when we have a positive value of time. I'm saying that now because I don't think we're going to get there before we derive all this other stuff. So now the signum function is this limit of x sub 1 of t as a goes to 0. That's now 1 for t greater than 0. It's actually 0 for t equal to 0 and minus 1 for t less than 0. Now, if you combine this with a constant, you can get a unit step. So that's where we would eventually want to go. But let me now just derive, let me go back. I haven't yet found the signum function. Defined the signum function. Let me just find the Fourier transform of little x sub 1 of t, where I have these nicely decaying exponentials on either side of the time origin or time axis. Let's see what capital X sub 1 is. But now I can break this up into two pieces. It has two functional forms. I have one piece from minus infinity to 0, and that was this minus e to the at piece, e to the minus j omega t dt, plus the other piece that was for the positive half of the time axis. That was e to the minus at, e to the minus j omega t dt. And that second integral I've already done. But the first integral, I'm now going to combine my a's and j omega. I now have the quantity a minus j omega, but I have that minus sign already sitting there. So this is now minus 1 over a minus j omega e to the a minus j omega t, evaluated from minus infinity to 0, plus what I have already done before, and what's this left term look like? As t goes to minus infinity, a is positive, and so this is going to vanish at the lower limit, isn't it? It's going to give me a non-zero value when I evaluate it at t equals 0. And that minus sign is going to stay. So that I now have minus 1 over a minus j omega. And I've already integrated or evaluated that second term, and that was just 1 over a plus j omega. So that's now the Fourier transform of this special two-sided decaying exponential. What happens as a goes to 0? I'm running out of time, so I'll just talk my way through it. I may put some of this stuff on. So now as a goes to 0, I have minus over minus j omega. That's just 1 over j omega. This is just 1 over j omega. I'm left with 2 over j omega. That's the Fourier transform of a signum function. And does that make sense? What is, in terms of magnitude, I have 1 over omega. That looks like this, doesn't it? Where is most of the energy? At the origin, at DC. And if I now had this signum function, what is it most of the time? It's constant, isn't it? But what happens right at t equals 0? It switches. And what's that switch do? Shakes everything at all these frequencies, doesn't it? That's what gives us the tails. That's the 1 over omega. We'll pick up somewhere after that on Thursday.